Okay, let's unpack this a bit. Have you ever really, really stopped to think about nothing?
Hmm.
I mean, not just, an empty room, but truly, fundamentally nothing.
It's a funny concept when you dig into it.
It's kind of a brain twister, right? Because even when we try to imagine absolute emptiness, our minds still sort of picture, well, something maybe just blackness.
Right, an absence.
Yeah.
But even that feels like a thing.
Exactly. But what if that absence of stuff, that emptiness, is actually buzzing with activity, like more activity than you'd believe?
Well, that's where modern physics completely flips the script on our intuition. The picture we have in our heads of this, serene, empty void, it's just not the reality.
Way more interesting.
Oh, far more interesting. Nothing turns out to be pretty complex.
And that's the rabbit hole we are absolutely diving into today. This deep dive is all about the quantum vacuum, this really mind-bending idea. We've been looking at Jim Baggott's book, Quantum Space, and honestly, it's the kind of stuff that makes you look sideways at reality.
It really does. And for you listening in, maybe you're curious about how reality works at its deepest level, but without getting totally swamped in equations.
Yeah, exactly.
Then this should give you some, well, genuinely surprising insights. We're aiming for those moments where you just go, aha, or wait, really?
Those moments that make the universe feel a bit more, I don't know, magical, even though it's science.
Precisely. It is
Yeah.
science, but it borders on the fantastical sometimes.
So, our mission today, which let's be honest, you've basically accepted by tuning in, is to unpack the key ideas around this quantum vacuum. We want to get to the heart of what it means, why it's important, without, tying your brain in knots.
So where do we start with something as weird as nothing?
Good question. Maybe we should start with how we used to think about space before things got weird.
That makes sense. To see how radical the quantum vacuum idea is, you kind of need the backstory. For centuries, really, thanks mainly to Isaac Newton, the picture was pretty straightforward. Space was seen as this absolute, unchanging container, like a giant empty box where everything else happened, a real independent thing.
Yeah, like a stage for the universe, fixed, solid, dependable. It made sense, didn't it? You throw a ball, it goes through space. Space just is.
Exactly. Newton's classical physics, which worked incredibly well for so long, relied on that idea of absolute space and absolute time. It was the framework.
The bedrock.
hmm But then, towards the end of the 19th century, people started questioning things that couldn't be directly measured or observed.
Hmm.
This sort of empirical philosophy was taking hold.
So ideas that were more philosophical, metaphysical.
Yeah, exactly. Concepts like Newton's absolute space and also this other idea, the luminiferous ether, they started to look a bit shaky.
Ah, the ether. I remember reading about that. That was the invisible stuff that light waves were supposed to travel through, wasn't it?
That was the idea. Like sound needs air, light being a wave seemed to need something to wave in. The ether was the proposed answer.
Makes sense, I guess.
But, well, the big problem was nobody could find it. The famous Michelson-Morley experiment tried to detect Earth moving through this ether
And
and found nothing. Zilch. No sign of the ether.
whoops. So much for the ether then. That must have been a bit awkward.
It certainly complicated things. So
Yeah.
you had this thing, the ether, that seemed necessary but wasn't there, and the old comfortable idea of absolute space was also being questioned.
Science loves a good puzzle, doesn't it?
It thrives on it. And this tension, this cognitive dissonance, really set the stage for Einstein.
Right, with relativity.
Exactly. Relativity basically said, hold on, space and time aren't absolute or independent. They're linked. They're relative to the observer. Baggott points out that Einstein felt this took away that last bit of physical objectivity from space and time.
Which is still kind of hard to properly grasp, even now. Gravity isn't some spooky force pulling things.
No, it's the curvature of space-time itself, caused by mass and energy.
Like the bowling ball on the rubber sheet analogy. The ball makes a dip, and marbles roll towards it because the sheet is curved.
That's a great way to visualize it. And general relativity made these incredibly precise predictions, things Newton's theory couldn't handle,
Oh.
like tiny details in Mercury's orbit.
And when those predictions were confirmed,
Baggott mentions Einstein had this profound emotional reaction, a real uh, cosmic aha moment, vindication.
this felt pretty good. But okay, even with relativity changing our view of space and gravity on the large scale, the really, really weird stuff was happening down at the quantum level, right?
Oh, absolutely. While relativity was rewriting the cosmos, quantum mechanics was uncovering this completely counterintuitive reality for atoms and particles. Probabilities, uncertainty,
Yeah.
just weirdness.
It's like light. Sometimes it's a wave spreading out, interfering.
Right, like in the two-slit experiment.
There's other times it's a particle, a photon, a little packet of energy, and then electrons do it too.
They do. The electron two-slit experiment is maybe the ultimate example of quantum weirdness. Fire electrons one by one, and they still build up an interference pattern over time. It's as if each single electron goes through both slits somehow and interferes with itself.
How does that even work? It's like it can't make up its mind.
It's just how the quantum world behaves. Wave-particle duality. It's fundamental.
Okay, mine's slightly blown already. But this quantum weirdness, it connects back to the vacuum, doesn't it? Through the uncertainty principle?
Yes, exactly. The uncertainty principle is key here. It basically says there are limits to what you can know simultaneously about certain pairs of properties.
Like position and momentum, if you know one really well.
You know the other one less well. And crucially, there's a similar relationship between energy and time.
Okay, energy and time. How does that make empty space not empty?
Well, the energy-time version of the uncertain principle implies something remarkable. For incredibly short moments, tiny fractions of a second, the strict law of energy conservation can be, let's say, bent a little.
Bent, you mean broken.
Not quite broken, more like temporarily borrowed. You can borrow a tiny amount of energy from the vacuum if you pay it back extremely quickly.
Like a cosmic overdraft, a really, really short-term one.
That's not a bad analogy, actually. And this borrowed energy allows pairs of virtual particles, like a virtual electron, and its antimatter twin, a positron or virtual photons, to spontaneously pop into existence.
Out of nothing.
Out of this borrowed energy, essentially out of the vacuum.
Yeah.
But then they almost instantly annihilate each other, paying back that energy debt.
Whoa. Wait, so empty space isn't empty at all. It's like this fizzing, popping soup of particles appearing and disappearing constantly.
That's the picture. Baggott calls it a chaos of wildly fluctuating quantum fields and virtual particles, like turbulent waves. On average, over time, it all cancels out to zero. Looks empty.
But at any single instant, at any point,
There's activity, fluctuations, energy. It's not zero.
that's wild. Is there any way to like prove this is happening? It sounds like science fiction.
Well, there's strong evidence. The Casimir effect is the classic example.
Casimir effect.
Yeah, if you take two perfectly smooth, uncharged metal plates and put them incredibly close together in a vacuum,
Okay.
the tiny gap between them restricts which virtual particles can pop into existence there. Specifically, the ones with longer wavelengths don't fit.
Right.
But outside the plates, all the virtual particles are still doing their thing. This difference in the vacuum pressure, if you like, creates a real measurable force pushing the plates together.
Hold on. So this nothing, this vacuum energy, is actually pushing things around physically.
It is. It's a tiny force, but measurable. It's seen as really solid evidence for the reality of these vacuum fluctuations in virtual particles.
Okay. My brain is officially stretched. So this buzzing vacuum isn't just sitting there, it's doing things. How does it connect to, say, forces like electromagnetism?
Well, that's another layer, those fundamental forces. They're actually mediated, carried by these virtual particles.
So when two electrons repel each other, it's not just magic.
Nope. It's because they're constantly exchanging virtual photons. These photons carry momentum, like tiny messengers passing the repel signal back and forth.
Huh. So the force is the exchange of these virtual particles.
In the quantum field theory picture, yes.
Yeah.
And it's not always just one simple exchange. Sometimes more complex things happen involving multiple virtual particles looping around.
Baggott mentioned radiative corrections
Yeah.
and Feynman diagrams. Are those related to this?
Exactly. Radiative corrections are the calculations that account for those more complex multi-particle virtual exchanges. They slightly adjust the probabilities. And Feynman diagrams are these brilliant little sketches.
Like cartoons.
Kinda.
Hmm.
They help physicists visualize and calculate all the possible ways particles can interact by exchanging virtual particles.
Mhm.
Incredibly powerful tools.
Okay, so forces are virtual particle exchanges happening in this busy vacuum. What about mass, though? Where does stuff get its weight, its heft? Is the vacuum involved there?
Yeah,
Check.
absolutely. In a really profound way, through something called the Higgs field.
The Higgs. I've heard of that. The God particle stuff.
Well, the particle, the Higgs boson, is related, but the key thing is the field. Imagine space, the vacuum, is filled with this invisible Higgs field. Unlike the vacuum fluctuations, the Higgs field has a constant, non-zero average value everywhere.
So it's always on, like a background hum, or like that syrup analogy you sometimes hear.
The syrup analogy is pretty good, actually. Now, different fundamental particles interact with this Higgs field syrup differently.
How so?
Some particles, when they move through the field, interact strongly. They get stuck or slowed down by it, like wading through thick syrup. That resistance is what we perceive as their mass.
Wow. So mass isn't inherent, it's an interaction.
It's an interaction with the Higgs field. Yeah. Particles that barely interact with the field, like photons, have little or no resistance, so they have little or no mass.
So the Higgs field is basically giving everything its weight by sort of dragging on it.
That's the essence of it. And finding the Higgs boson at CERN a few years back was huge because the boson is like a ripple, an excitation in that field. Finding it confirmed the field exists and this mechanism is real.
Incredible. So the vacuum, this emptiness, is where forces happen and where mass comes from. It's doing all the heavy lifting.
Pretty much. It's fundamental.
Okay, but quantum space also mentions quantum gravity. Where does space-time itself fit into this quantum picture? Is it part of the vacuum fluctuations too?
Now you're hitting the frontier. This is where things get really speculative, but also deeply fascinating. Theories like loop quantum gravity suggest that space-time itself isn't the smooth, continuous background Einstein described.
Not smooth. What is it then?
It might be quantized, made of tiny, discrete chunks or loops at the smallest possible scale, the Planck scale, like atoms of space and time.
Seriously, so space isn't infinitely divisible.
That's the idea in loop quantum gravity. And importantly, it describes space-time using a quantum field that doesn't assume a background stage to exist on. It generates space-time itself.
Unlike regular quantum field theory, which happens in space-time.
Right. LQG tries to quantize gravity, the structure of space-time itself. There was also an earlier idea, maybe more intuitive, called quantum foam.
Quantum foam. Sounds messy.
Yeah, the idea that if you could zoom way, way down, space-time would look like this churning, chaotic foam of quantum fluctuations. Loop quantum gravity gives a more rigorous mathematical structure to that kind of idea.
This is just a complete overhaul of reality. We started with Newton's empty box, and now we have this dynamic quantum void that's not void at all, giving rise to forces, mass, maybe even space and time itself.
It's a profound shift. It really shows how limited our everyday intuition is when it comes to the fundamental nature of reality. What looks empty and passive is actually the most active and fundamental stage there is.
So let's try and wrap our heads around this one more time. This nothing, the quantum vacuum.
It's absolutely packed. It's governed by quantum uncertainty, fizzing with virtual particles that carry the fundamental forces.
It's permeated by the Higgs field, which gives particles their mass by interacting with them.
Right. And potentially, at the very deepest level, it might be composed of the quantized fabric of space-time itself.
It's amazing how understanding this, even just conceptually, opens up so much about modern physics. It really is like getting a key to a deeper level of understanding the universe.
It is. And hopefully you listening now have a sense of that a glimpse into a reality that's just so much stranger and frankly more wonderful than what we see day to day.
But it definitely leaves you thinking, doesn't it? If what we thought was nothing is actually this incredibly rich something full of potential.
Mhm. What else are we wrong about?
Exactly. What other basic assumptions about how things work might just dissolve when we look closely enough with the tools of science? It really highlights the limits of just trusting our gut feeling about the universe.
And the power of asking questions, of probing deeper, even when the answers seem completely counterintuitive. The universe still holds so many secrets,